Hello again, everybody, and welcome back. This chapter, chapter 10, is on rotational kinematics and energy. And while the title may sound like a mouthful, you've actually had kinematics and you've had energy before. So this is simply going to be in the rotational sense. So there's going to be a lot of analogs or comparisons to stuff that you've already learned, but it's simply going to be for objects that are rotating. So let's just go ahead and get started. So our first idea is angular position. And if you recall in kinematics, one of the first things that we learned about was simply position. That is, so here's your origin right here. Okay. And you start at maybe position 1, that's 2 or position initial, that's 2 meters. And then you move to position final, that's 5 meters. Okay, we learned that's one of the first things that we learned. Well, angular position in linear or one-dimensional kinematics is with regards to the origin. So this is 2 meters from the origin, that's 5 meters from the origin, okay? But angular position, that is position around the edge of a circle, first of all, is measured not with x, but with what should be a familiar character to you, theta, all right, it's an angle theta, but it's made with regards to what's called a reference line, all right? And let me mention the bottom part real quick right here before we skip to the next slide. If we go this direction from the origin, it's positive, and if we go that direction from the origin, it's negative. Well, the reference line that I'm about to show you, if you go clockwise from it, it's considered negative, and if you go counterclockwise from it, it's considered positive. I just want to mention that right now so we didn't have to flip back to this slide, but really the diagram I want to kind of mark up is on the next one. So I'll try to make some sense of this. All right, so we have a bicycle wheel, a very common kind of sort of everyday item, and this line right here is our reference line. I guess you can make it wherever you want, but very often you'll see the reference line be in the 3 o'clock position. But it could conceivably be from anywhere. But it's a line that your object is starting rotating from, right? Very much like you could call that like your origin. All right, think of it like that. But the object doesn't move in a straight line from the origin; it moves in an arced line. And so this is our rotational change in position. So if it goes counterclockwise, we call that positive. All right, and if an object moves, now I'm getting mixed up. If it moves clockwise from that reference line, you can also think of it as the origin. We call that a negative change in position around the edge of that circle. Okay? So, the amount that this red dot or blue dot or whatever it is on the edge of the circle has rotated around the edge or has changed position around the edge is measured as an angle. Now, up to this point, we have been using degrees to measure angles. And it's at this point that I'm going to say, okay, take your calculators and change from degree mode now to radian mode. Because the next 2 chapters, we're going to be dealing with angles based entirely in radians. And while 360 degrees may be familiar to us in terms of breaking a circle up into all kinds of different little slivers, a radian actually probably makes more sense. Because what a radian is, it's, let's say this red line right here, let's say that's a radian. That's like taking a radius and stretching it and bending it around the outside of a circle. It's really a radius along the edge. Now what that means is that a radian doesn't necessarily have a set length because no circle has a set length. Well, look at this right here. I mean, our bike tire, around the outside edge, this arc, this theta, produces this length of radian along the outside edge for this red dot to displace or change position, all right? But if our radian is now this smaller arc right here, if our radius is that smaller arc, and so we make the radius be not a very good circle based on that radius, is it? But if that is a circle based on that radius, then now all of a sudden, this smaller little arced line right here is a radian for that circle. So a radian doesn't have it's a unit, but it doesn't have a set distance. It has a set distance around a specific circle, but every single circle has a different radius. What's important to know and you may recall this from math, is that one distance around the whole circle, also known as circumference, equals 2 pi. Well, in math you probably learned it was 2 pi r, whatever the radius is. But if you were to stretch that out into a straight line, that would be 2 pi times the radius, but we call it 2 pi radians. 2 pi radiuses, or radii, around that circle right there. So we should really say 2 pi, oops, not rad, R-A-D, radians. That's what we have down here at the bottom. It is true that one revolution equals 360 degrees, but we're going to bypass that this chapter and say, all right, one revolution is 2 pi radians. Of course, you know the pi is 3.14 and some change, so 2 pi is going to be 6.28 and some change. So that's going to be, let's just say we had a bicycle wheel with a 1 meter radius, and that means around the edge it would be 6.28 meters all the way around. And the same proportions are true for every single circle. But for every circle, a radian may be slightly different because it may be a different sized circle. But get used to using radians and converting to and from revolutions. Radians are going to be kind of the universal unit because every circle has a certain sized radian based on its radius size. Okay? So, if we have a position here and a position there, we have to have a change in position, right? We say a displacement. Well, in 1D kinematics, we had a displacement going along a straight line, say from 2 meters to 5 meters. But here we have from our initial theta to our final theta. All right, whatever our initial theta is with regards to the origin. Let me just draw a quick circle here. Unit circle. All right, so there's our circle, and there's our reference line right there. You don't always have to start at the reference line, but if your initial theta is here, theta initial, and you move to here, that's our theta final. So there's our initial, and there's our final. That's going to give us our change in angular position, also known as angular displacement. So it's very much like x initial, x final, and delta x, but it's around the edge of a circle. So this is our displacement around the edge of that circle right there. All right, so it's the final minus the initial. Of course, this takes time. You can't change position instantaneously. So if this takes place over a certain amount of time, or delta t, for this delta theta that we have right here, delta theta, delta t. Well, if we put delta theta over delta t, that's very similar to saying delta x over time, right? And we know that from one-dimensional kinematics as being velocity. Well, around the edge of a circle, we call this the angular velocity. And this is the Greek letter, it looks like a W, but it's called omega. It's a lowercase form of the omega that you've probably seen that looks kind of like that, but it's called omega. All right, and that is going to be our angular velocity. If you think of it, it looks kind of like, well, it looks like a W, but think of it as looking sort of like a V, and V for velocity kind of gives you that sort of reference that it's just like velocity. But instead of meters per second, it's radians per second. And since a radian doesn't have a set distance or set value, you could say that angular velocity is simply seconds to the negative first, or that is something divided by seconds. Because remember, every radian is going to be different. But a radian is a set amount for a set sized circle. So this equation right here, our average angular velocity, is a change in angular displacement, or it's our angular displacement over a change in time. This over on the right is a more calc-based version of deriving this. What we're going to mostly deal with is the average angular velocity. But this would give you your instantaneous angular velocity at a certain point in time. All right. Well, so let's wrap up this segment by doing a couple of examples, and we're simply going to be converting from a rate of angular velocity to another form of that. Okay. So let's take a look at example 10.1 and 10.2. So we have an old phonograph record. That's the same thing as an LP or a vinyl record. And it rotates clockwise at 33 1/3 RPM. Well, you probably know that means revolutions per minute. And what that is an angular velocity. It is a certain angular distance over a certain amount of time. But we want to turn this into radians per second. Incidentally, 33 1/3 may seem kind of arbitrary, but that was actually a very common rate of speed or rate of angular velocity for a large LP record. So that's not arbitrary at all. It's a common value. So let's take this and let's turn this into radians per second. Well, let's write it out. 33 1/3. I'm just going to do 33.3 RPM, revolutions per minute. All right, we want it to become in radians per second. Okay, so let's take, this is really going to become a sort of a factor label problem, so let's take revolutions and turn it into radians. All right, well, we know that one revolution, or one circumference, equals 2 pi radians. 2 pi radians. All right, so that means our revolutions goes away and we have our radians in the numerator. And let's take our minutes and turn that into seconds. We know how to do that. 1 minute equals 60 seconds. So seconds is going to be in our denominator because minutes cancels out. Let's just crunch our numbers and see what we get. So I took 33.3 times 2 pi divided by 60, and I get 3.49 radians per second. Now that could be that is the rate of motion that the record is spinning at right there. But if you think about the edge of the record, let's see if I can get my my black pen right here. Here's our record. Sorry, I don't have a whole lot of space to draw, but the edge of the record, that is 3.49 radians per second. This also here, so going from here to here, that's 3.49 radians per second. If we go from here to here, my goodness, that is really, really small. You know, I'm just going to erase that and make it a little bit bigger because that is not very helpful. Let's make it a little bit bigger, and I'll do it down here in the corner. I think I'll be able to have enough space. There we go. Okay, so so from there to, well, 3.49 radians is more than one circumference, but let's just say it was is a lesser amount. Whatever it is in radians per second, the edge of the record is moving at that speed, all right, that distance per second. And the middle part of the record right here, so the edge point is moving around here, a certain distance per second. The middle point right here is going to be moving like so. And it's much of a less speed, you might say, or much less actual distance per second. But we need to point out that these have the same angular velocity, it's the same number of radians per second. It is the same angle theta per second. Whether it's 1 radian, 2 pi radians, or 3.49 radians, every part of that record is rotating with the same angular velocity. We're going to get to a linear velocity later on, and that's what's going to be different. This clearly is covering more space in a certain amount of time. So a different kind of velocity is going to be true of here than here. But they do, for now we are going to say that they do have the same angular velocity. It's the same change in theta over time. Okay? All right, let's do the CD real quick and then we'll be done. So it is rotating at 22.0 radians per second. Let's convert it to RPM. All right, and going from RPM or revolutions to radians is going to be something you're going to need to do a lot because radians are going to be kind of the common factor with all these circles right here. So radians to revolutions, right? Radians to revolutions. Well, we know that 1 revolution equals 2 pi radians, so that conversion is done. Radians goes away. And seconds, 60 seconds is 1 minute. And again, you should probably know that RPM means revolutions per minute. And so that's going to be our final value. So seconds goes away. So now we have it in revolutions per minute. Let's just punch our numbers in and then we'll be done. Okay, and I get a value of 210. 210 what? Revolutions per minute. You can write it in rev per min, or you can do RPM. That's fine too, but writing it out as kind of a vertical fraction helps you to kind of cancel out those values. That lets you do the factor label correctly. So that's our first examples in angular or rotational kinematics, I should say, and we've just converted from one rate of angular velocity to another, and we're going to be doing that a lot more in the future. So for now, thanks for following along, and I'll see you on the next one.